Hey folks, how's everybody doing today? Happy Thursday. Alright, we are finishing up our look into priority queues today. Let me fire up PyCharm here. Let's see. I'll fire up Canvas too. Take a peek at our schedule. I think we're doing well. Moving through the material. We've got that last individual project we've been working on as well. Hopefully you had a chance to get that one started. It's our polynomials, right? Let me pull this up here. Alrighty. Yeah, push login, please. Let's see if I get logged in here. There we go. Alrighty. Come on, Canvas. Of course, now it's gonna be slow, right? There we go. All right. Let's see. Get the polynomial, April 1st. We still have some time on that, but definitely get started on that one early. This one's a little funky, dealing with linked objects. We got 2 weeks from today till that one's due. And that'll be our last individual project, and then we'll have the final project coming up all of April, and you're welcome to do that one in pairs if you'd like. Again, I'm not going to require it. Usually I would if we were in person, but it's just, you know, the nature of this async optional or synchronous optional is it makes teamwork a little tough. Usually we would have time after class or in lab, you know, to get together and work on stuff. So we're done with that. and quizzes. I gotta remember to keep posting quizzes here. Didn't I? I didn't post the quiz. Okay, I'll post one on priority queues when we're done with this. Let me add this as a note here. Post for priority queue. Priority. That's right, if I don't spell it right. So we didn't quite finish our priority queue. We got close. So we talked about this idea that it will keep the minimum item at the top there. And then we have some rules to keep ourselves in heap structure, in that our children here, because we're binary tree, our left and right children, they must be greater than or equal to me. So we're not a unique set. We're allowed to have duplicate values here, which is okay. Okay, so we add an item then. Right, we're going to make a new item out of it here with this little private item helper class here. So we have our key and value, so we're going to create a new item. We have our item equals self.item, given the key and the value. Okay, and now the rule for priority queues, right? How we do this. There's this fun process that I think is amazing. It has the best term. Priority queues are like heaps are my favorite. You up heap and you down heap. So when we add an item, remember what we're doing internally is we're storing ourselves as this array-based storage, this data storage here. So first we need to make sure we have room when we're adding items. Okay, so we can check to see if our self.number of items is greater than or equal to the length of self.data. I mean, really, I guess it really just equals. We're only adding one thing at a time. So if we've maxed out, if our number of items is the length, we don't have room. So if our length is 1, then we don't have room to add a second. Oh, that's okay though. So we'll do that first. That's right. And then we'll add to the number of items. So if we have one item and we're trying to add another, we don't have room. So we need to increase capacity. Self.increase size. And we'll go to, remember we just need to add, we need to double this idea that every row, right, every generation here is twice as many items as the row before. So we have one item in the first row, 2 items in the next row, 4 items, 8 items, 16 items, on and on and on. We kind of sketched that out, right? So we need to increase our size here to make sure we have room. So we're going to increase our size here. So we need a little helper method. So we'll have a define increase size. What that means is I need to make a new list, right? We did this doubling thing before, and then we need to copy everything from the old list into the new list. Right, so we did this way back when did we do this check capacity? I feel like we did that. 2001. Let's take a peek. We have this like check capacity or something, don't we? Check capacity. I think we did that with our array-based list. Yeah, here we go. Check capacity. There we go. So let's just copy this one here. It's not exactly everything we need, but that's okay. So, oh, okay, that was even just checking. I like that. So that's fine. We already know this is going to happen. We were just calling it here. We had new data here, and I don't think we need any of that then, right? Oh, that's the other loop. Okay, so that's fine. And I don't think we need the new data index either. So we'll say for item in self.data, or we need the index. Yes. For index in range length of self.data. We're going to copy them up. We're going to say new data at index is now going to be equal to self.data at the index. So we do the copying. Right? We double in size and we do the copying. Right? Because remember when we sketch this out, the size of our tree here Right, let's clear this one off. When we had one item, right, this was total size. This was size. Here's 1, and then when we add more, right, our size is 3, and we add 4 more, right, our size is 7, and then we add another one. So we're not doubling every single time, but that's essentially what we need to do to make room for these, okay? And if we do the doubling, we're always going to make sure we have enough room, so we can copy all those over. Remember, each one here then is 2 to the height number of items. So this one has 1 item, this one has 2 items, this one has 4 items, and then 8 items, on and on and on. And when you sum those up, you get 2 to the height plus 1 minus 1 is the size here. We can always calculate our size here in our max storage. And we just copy them over. Okay, and then we need to say self.data equals the new data. Okay, so we've increased in size, we've copied over. Then we can increase our number of items. We make a new item here. Then what we need to do is we need to do our upheaping process, because we're going to add it in at the end here. So the number of items. So when we had 0 items, it goes at index 0. When we have 10 items, it's going to go at index 10. So that's actually before we add that. We're going to add that after. We'll make the item, and then we'll go throw that into data, so self.data, at the self.number of items is equal to the item. We put the item in there, so we put it at the end. So as we start adding things to our heap here, right, so say we had like 7 and 12 and 15 and 19 and 13, I probably don't even need the circles. Let's just go up here. So let's add a bunch of items. So 7, 12, 15, 19. Oh, sorry, this direction. 18, 13, 19. So we go add an item here. We're going to add it to the next available position. Remember, we're keeping this tree structure where we are a complete tree, where we're filling in from the left every row at a time, every generation at a time. Okay, so if we were to go add, say, a 6 here, we need to make sure we stay in heap form. So we add an item and then we upheap it. So what we're doing is we're upheaping this. We're saying, hey, if you are smaller than your parent, swap. So we swap with the parent. So we will swap 15 and 6 here. We put 6 in here and we swap 15. We say, hey, if we're smaller than our parent, swap. So we're going to swap 6 and 7. So what that means is anytime we add an item, the most number of operations we're going to do, right, is log n. Because log n is logarithmic based on the height. So the height of our tree is the most number of operations. And we know the height of our tree, right, it grows logarithmically because we're filling every single row. I think we looked at that proof, right? When we looked at how many items we had in here, we just add a bunch of things, 1, 2, 3, 4, 5, 6, 7. So as we add items, right, the height only increases every time we double. So right now height is 0, height is 1, height is 2, and I have 1 item, I have 3 items, I have 7 items, I'm going to have 15 items next, right? 7, 8, 9, 10, 11, 12, 13, 14, 15 here as those children, right? Because each one of these, because we're filling left to right, we're a complete tree here. We'll get 16 and 17 and 18 and 19 and 20 and 21 and 22 and 23 and 24 and 25, 26 and 27, 28, 29, 30, 31. Right? So the height of our tree is going to grow logarithmically if we keep it in a complete form here. That's the goal. So the adding an item is at most, worst case, logarithmic in n, because it has to go all the way to the top. So our average time is still logarithmic in n. We add an item. So adding here then is O of log n, which is nice. That's a nice fast operation, right? Growing logarithmically is nice. Okay, getting the minimum item out, right, is O of 1, because it's always at the top. Right? The smallest item is always the top of our heap here. Okay? So what we're going to do is when we add an item, then we're going to upheap. So we call self.upheap. And what we do is we upheap at that index. Okay? So let's take a look. We need to add that little helper method here. So we're going to add self.upheap. Upheap for self and an index. Oh, sorry, that's define, not self. Upheap, self and index. Okay? Upheap. Why is it not like that? Typo. That's fine. That's fine. Upheap is okay. I don't mind that term. So what it does is it checks, hey, am I smaller than my parent? So we need, again, we have to have those parent definitions here. So define parent of an index, right? Remember we looked at that was going to be 1/2 rounded up. And when we looked at all of those, when you looked at your indexes, you take half rounded up, and then you subtract 1. So at index 1 or 2, you take half of that rounded up is 1, minus 1 is 0. Remember we did all that last Tuesday? Okay. So we need to take the index, so parent is equal to the index divided by 2, and we need to round that up, right? So we need math.ceil, I think was that it? Math.ceil minus 1. We got to import math, right? Import math. Okay, and then we can do math.ceil, right? So ceil is the ceiling, so it'll round up here, minus 1. That's the parent. Okay, and then we can check. So we can say if self.data at the index is less than self.data at the parent index. Sure, we'll call it parent index. If it is, right, and remember these are all items, and we've defined an item less than. We're just comparing key. Is the key less than the other key? Okay, if we're less than, we swap. We're going to swap them out. So we're going to say self.data at index is temp equals that. Self-data index, and then self.data at index is now equal to self.data at the parent index. And then self.data at the parent index equals temp. Now, you can also do this with one line. Python lets you do this as a one-liner, which always confuses the crap out of me. But you can say data at index, comma, data at parent equals the parent, comma, the data. I don't like this one-liner because this confuses me. One-liner. Because Python is awesome. Sure, you'll say set this thing to this thing and set this thing to this thing. And when we swap them, it'll do them without overwriting the wrong way. I get confused by that one. So I'm just going to comment that one out, and we're going to do the swap the hard way. So that's swap, right? Okay. Then what we do, if we're less than, then we call self.upheap. I'm sorry, nope, self-parent, all you need to do is return parent index. Oops. Upheap needs to get that. There we go. So we get the parent index is equal to self.parent of the index. And then we can do this here. Okay. Just saving us some time here. Here's that one-liner. Then what we do is we call upheap again. Self.upheap given the parent index. So this is recursive. So we go add an item. When we upheap it, right, we say, okay, if we needed to swap, recurse at the new index, the parent index. If we need to swap, okay, do it and then recurse at the new parent index. So we do want to stop, though, when index is 0. So if index does not equal 0, right, then we can keep on doing this thing. If we hit 0, we're done, right? That's the smallest item here. So this is what stops when index is the top of the tree, of the heap. Because I know there's no parent. okay? Then we'll get the parent index and we'll do the swapping. If we're not less than, we're done, right? Perfectly fine. So if we have our tree structure here, and I were to add an item to this tree here, so it'd be this child, because we're at the complete form. If I were to add a 20, we're done, right? No big deal. Perfectly fine. There's no change that needs to happen here, right? So sure, that just adds. Okay, that's the upheap process. So when we add an item, we upheap it. Okay? Then what we do when we remove an item, this is the fun part. When we remove an item, what we're going to do, and actually I want to add another helper method here because I'm tired of doing this a bunch. So we're going to call swap index and new index. Right? If that's it, then I want to do the swap thing. And index, new index, and new index. There we go. So we'll just call self.swap. Because we're going to do this a bunch. Okay, we're going to do this a lot of times here. So let's swap the index and the parent index. Okay. And I guess we'll put that one-liner in here then, right, because that's where this belongs now. New index. Sure. So we swap them and then we upheap. Okay, so to remove the min, what we do here is, remember, we need to keep this tree form. So if I want to remove the item from this tree here, let me rewrite it here. Right, so we had what, 6 and 7 and 15 and sorry, should draw all the lines out there. 19 and 16 and 10 and 11, and we had what over here? We put a 20 in or something, right? So if I were to remove the minimum, what we do is we swap the first item with the last item because we need to maintain our tree form. Okay, so we're going to swap these two here. So I'm going to put the 6 down here, and I'm going to put the 20 up at the top. And then I can remove the 6, and I can give it back when we're done. Okay, so we can actually pop that one off. Then what we do with this 20 is we downheap. And downheaping makes sure that we stay in proper tree form, or heap form, right? That we are greater than or equal to our parent. All right, I think I'm back. Maybe. Okay, sorry about that. I don't know. I killed my Wi-Fi and turned it back on. That was weird. Maybe that wasn't Comcast. I don't know. Okay, so once we swap, then we can downheap. Where we pop off the item, we downheap. So remember, we have 1, 2, 3, 4, 5, 6, 7, 8 items here, right? That's at index 0, 1, 2, 3, 4, 5, 6, 7. So index number of items minus 1 is what we're swapping. Okay, and then we have the item to return is self.data.pop. And we want to pop a particular index, right? So we want to pop the self.number of items minus 1. Or really, we don't even need to pop it, right? What we can do is we can just take that index value here as the item, and then we can none this out, right? Because we don't need to actually resize our internal data storage. We can be oversized, and that's okay. Not going to be too big of a deal for us here. We'll have that as the item here, and then we've nunned it out, and then we need to start downheaping. We call self.downheap on index 0. Okay, so we need to write downheap. So what does downheap do? So we're going to define downheap that takes an index. Okay. So downheap, we need to figure out children. So we need a left child and a right child. Left child given an index, and define right child given an index. Remember, your left child was u times 2 plus 1, so we're going to return index times 2 plus 1, and your right child was index times 2 plus 2. Right? Remember, we did all that, the chart over here with your children here. So at index, we had parent, child, left child. So at 0, right, 0 times 2 plus 1 is 1. 0 times 2 plus 2 is 2. So index 0, 1, and 2, that's left and right. And then at index 1, right, 1 times 2 plus 1 gives me 3, right, that's index 3 over here. 1 times 2 plus 2 gives me 4 over here. And this, we worked that out. We said, okay, all that math checks out. We're happy here. So when we downheap, what we do is we need to check. We need to see if we are less than our children or not. Okay, so the first one, we're going to check. Right, we can see if we're less than, well, really, we need to get our index and see if it's within bounds as well. Right, so the index should be less than the number of items minus 1. We check for is valid index given an index, and we're going to return index is less than less than self dot number of items. Right, if we're less than the number of items, it's a valid index. And also, right, and index is greater than or equal to 0. How about that? Right, that means it's valid. Right, just in case. Both are fine. Okay, so really, yeah, we'll just return this here. We'll just return. We'll save a line. Those are all one-liners, arithmetics. Okay, so for downheaping, we need to check if the right child is a valid index. And so if self dot right child of the index is valid index. So self dot is valid index. Whatever I get back from right child. Okay. So and really what I want is the smallest child. Here we're going to start off at none. If the right child index is valid, then I'm going to assume my smallest child is self.data at self-right child. So if I have a right child, if that's valid, then I'm going to assume that's the smallest until I know otherwise. And if I had a right index, a right child, I must have a left child. Remember, we're filling these in left to right. So if there is a right, there must be a left. Then I can check. I can see if self.data at the left child is less than the smallest child. Then my smallest child must be what's at the left. Remember, to keep the heap form, we have to be less than or equal to our children. So I can't swap with a child who's larger. I have to swap with the smallest child. Right? Right. If the right was not a valid index, then I want to check elif the left is a valid index of my left child. If that's a valid index, well then my smallest child is the left one. Okay? Right? So either smallest child is the right, or the left was smaller than that, or if I didn't have a right child, it's got to be my left child, if that's valid. If it's not, then it stays as none. So we check. So if smallest child is not none, then we look. We say if self.data at the index is, now we want to be swapping with the smallest child. So if the child is smaller than us, really, so if smallest child is less than us, then we're going to swap. We're going to call self.swap. Oh, shoot, this needs to be the index. Bummer. This needs to be the index. Smallest child. Because I need the index value. That's right. So we need index. That's self.data at the smallest child index. And it's just the right. Okay. If the left child is less than the current smallest, right, then it'll be the new less index. Okay, smallest child index is the left. There we go. So if the index is not none, okay, then self.data at the smallest child index is less than mine, then I can swap. And we're going to swap smallest child index with the index. Okay. All right, so what this is doing, right, we're trying to see which one is the smallest. If we have a right child, we'll assume that's the smallest, and then we'll check, hey, is the left actually less than the right? Because if you have a right, you have to have a left. If you don't have a right, we'll see, do you have a left? If you have a left, but you didn't have a right, well, obviously the left is the smallest child here. Okay? Then if we have one, then we want to go swap. If we're less than. If we have a child, the smallest child, we'll see, hey, is that smallest child actually less than us? Because if it is, we need to swap to maintain our heap rule. Then what we do is we recurse. We call self.downHeap. Self.downHeap given the smallest child index. So this is that recursive call. So if we have a child, so let's see. So we put 20 up at the top, and we're going to downheap. So it's going to look and see, okay, well, I've got a child of 5 and I have a child of 7. Well, I have a right child, so I'm going to assume smallest is, the index is 3, or I'm sorry, 2, right? 0, 1, and 2. And then we'll say which one is smaller, the left child or the right child? Well, the left child is smaller, so the smallest child index here is 1. And I'm going to swap. So I'm going to put the 20 in place of the 5. 5 and 20. Right? And then I'm going to recurse down heaping at index 1. So index 1, we're here. We say, okay, well, let's see, do I have a right child? I have a right child. Its index is 4. Is the index 4 item at index 4 less than the item at index 3, my left child? No, so the smallest child here is 3. Index 3. Is what's at 3 less than me? Yes, it is, so I need to swap. I'm going to swap the 20 with the 9. 20 and 9. Okay. We do need to make sure that when we remove that item then, before we downheap, we take self.number of items. Here we go. There we go. I like this. So let's do this first. Because I keep subtracting 1 from all of these things, right? So I'm going to take self.number of items. I'm going to subtract 1 from it first, and then I can get rid of all these extras, which is nice. Okay, and then when I downheap, right, the number of items will be correct because we've already removed that one. After we downheap, right, we do all of the downheaping, then we're going to return item. Okay, why does it not like parent? Oh, that's fine. Yeah, it says they can all be static. Like, we don't actually need the instance of self. That's okay. It doesn't hurt anything. I guess we could make them static, but okay. Expected list of none. That's weird. That's okay. This will probably work. We'll see if this works. Data parent index. Oh, because our list was, we started off with a bunch of nones. Okay, so let's see if we can do this. So let's look at, so how long does it take to remove something then? Right, when we remove the smallest item, again, the most number of swaps is going to be the height, which is O of n. Right, so this is O of log n, sorry, of logarithmic in n, because we know our height grows logarithmically with our number of items. Okay, so we'll see if we can add a bunch of items. So let's make a priority queue. Priority queue equals a priority queue. Okay, and then let's add a bunch of numbers. So we'll say for number in range, I don't know, let's add like 20 things. Why not? Here. Let's also import random, because this will be fun. So let's import random. Okay, we're going to take our priority queue. Nope, priority queue, and we'll call add random dot next, right? I don't know, let's go up to say 100 or so. Let's see what we get. And then while priority queue dot is empty, not, right? Well, oops, while not priority queue is empty, let's print priority queue dot remove min. We'll take them all off. Okay, let's see if that works. Crossing my fingers. Come on, right click, run. Nope, 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 nope. Right click, run. There we go. What we should get back out is a sorted order. Oh dear, it's not next. Random dot rand int. There we go. 100. Random dot rand int. From 0 to 100. There we go. Oh dear. That's right. Move in, and that is an item that we're returning. So we need to get the key, right? Because we're giving them a key and value. Is that right? Because when we add items, we're making them into, we turn them into items. Item.key. Is that going to work for us? Nope. It's shoot. Underscore key? That can't be right. That's ugly. Okay, it gets that's not the proper way, but it gets the number back out. And notice what we get is a sorted order. We get all these out in sorted order, right? Because we put the minimum item at the top every time because of the downheaping process, or the upheaping. When we add it, we upheap. When we remove, we downheap. So all those calls then happen logarithmically in n based on our size, right? Adding and removing is logarithmic, which is way better than when we looked at just a generic tree, right? Because there was no guarantee that the height wouldn't be size n, right? That a right child would have a right child, 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 on and on and on and on. Right? There's no guarantee. All right, so that item, oh, that's what we do. So we return, here, when we return those items, return item key and item value. Let's do that. Data is key and data's value. Okay, so we can just unbox them here. That should be fine then. If I just want the one item, I think I should get out just the keys. All right, we get a bunch of nuns. That's fine. We can clean that up later. But that's a little bit better. Right, so we never did any associated values, but we could use this as a mapping type. Right, we could have a key associated with a value, and we would get them in sorted order, which is pretty cool. Right, so what we're doing is we're using that heap property that says, okay, I will always be less than or equal to my children. So that means my children are always greater than or equal to me. On and on and on and on. And then we always add to the back, take from the top. And we add to the back, we upheap it, we take from the top, we swap, and then we downheap it. Right? That maintains our heap order. And again, duplicates are okay, right? We had, oh wow, a couple duplicates there. 57s, 54s, 49. Wow. 3 duplicates in a row. That's fun. Okay, that's what we get with our priority queue. Does that make sense? A little bit? And how we get this performance out of it. So it performs a whole lot better. The book really briefly talked about, oh, we could do it with a list, as a sorted list or an unsorted list, and which ones were slow. Or if it's a sorted list, it's slow to add. If it's an unsorted list, it's slow to remove. That sort of process. And all of those are n, O of n. So being able to get logarithmic in n is way, way, way better. Right? Because, if we're dealing with a large number of items, then we're really getting a gain out of it here. All right, let me pull up our text here, make sure I didn't miss anything. And yep. All right, yeah, those are pretty good. So we look at all those performances. The heap is good, using that tree structure. The book calls it bubbling. I like downheap. Downheap and upheap. So they do the Python implementation. Oh, there we go. So it took for parent here. I like that. He was smarter. His parent operation. So instead of saying this rounded up, he took the index -1 floor divided by 2. There we go. And that should give us the same value here. Yep. Okay, that math is a little smarter now. So -1 on your index and then divide by 2. I like that. He uses J for index, which drives me crazy. Drives me crazy. I don't know why. That's fine though. Okay, swap down heap. I think we're in good shape there. We did all those in our down heap. We would swap if we're less, and then down heap. Yep. Cool. Okay, he went in a different order, which is fine. He checked if you have a left child, you must have children. Go for it. I went from the right. Either way is okay. Add a key and value. And we return the keys and values. Cool, cool, cool. And again, we get that log n performance. One cool thing that you can do, if you know you have a large set of data and you want to put it into a heap form, turns out it actually performs better if you build it from the bottom up. You start with your largest row and you start adding items. And it's not anything we need to look at. I think you'll cover that in data structures and algorithms analysis if you continue on. But just know, that's a trick there to make building this a little bit faster when you do a bottom-up construction. And Python actually does have a heap queue module, which is cool. So you can use a heap. It's built in. And it's got a really cool method called heapify. Given a list, it'll turn it into a heap. So if you take an unordered list and you heapify it, it'll run in O of n performance, which is pretty cool. So just something to think of there. And we can use priority queue to sort things, like we looked at, hey, we get our sorted items out, which is fun. Cool, and then adaptable where you have locations. That's a little bit awkward, so we're not going to bother with the adaptable one either. Okay. So what we're going to do come lab time, thankfully heap wasn't so bad here, we're going to make a max priority queue. Right now this was the min priority queue. This is really a min priority queue here. And I can get rid of math, nice. Because we're always comparing less than items. You can make a max priority queue, which would sort on greater than. So it reverses the rule. It says, hey, you are always greater than or equal to your children. And I want the top item to be there. So that's what we're going to look at for lab, just as a sneak peek for that. So we're going to try and implement that. So maybe we'll call this a min priority queue. Okay? Or minimum, right? Minimum priority queue. I just need to go change that name over here. Minimum priority queue. Everything works the same except that comparison, right? To see, hey, do we swap if we're greater than versus less than, right? For our down heaping, right? If we're greater than, we need to swap other than, right? And then when we upheap, same thing. If we're greater than, we upheap because we want the greatest item at the top. And we want the smallest items at the bottom when we down heap. Okay? All right, I think that's all we've got for today. Don't forget the polynomial project is due in 2 weeks. Please start early. I seem to keep having trouble with people starting projects late, and then the day before it's due or the day that it's due, we have lots and lots and lots of questions. So, please do remember to start. And I'll post a quiz on priority queues. I've got my note here to post that for you. And that's all we've got today. So the lab hopefully will be nice and straightforward. Just a couple edits here to do our queues. Just a chance to play with it there. And we can go from there. All right, looking forward. We don't have too much else. Let's see. Let's take a look at our syllabus here. So we got priority queues. And then after that, we're looking at maps, right? Let's see. What's in the schedule? I always go look, because I can never keep all this in my head. Yep, maps, hash tables, skip lists. Most of that we're just going to do is maps. The skip lists, we actually skip. It's a cool thing, but we don't need to get into the details. Maps we were kind of doing, right, with the priority queue. Here's the key and associated value. Hash tables are fantastic. We'll spend most of our time on hash tables. Then we'll come back to those search trees, the binary search tree I kind of got into because I got excited, a little bit on sorting and selection, a little brief ethics seminar, lecture. I don't know, seminar is probably not the right term. And then time dedicated to work on the final project for you folks. A couple of classes reserved for that. Okay, and then ideally what we're going to do on 428 is we're going to get together and we can show off our final projects all together on like a Zoom call where you all can take turns sharing screens and it'll be just us. I know it's been async optional, synchronous optional, so if you really can't make it at this time, we can look at some alternatives, but given how we usually schedule our final exams, I think we'll be fine to do it this way. That block should be free for you. So, and we'll talk about more of that in April when we get there. So we still have a little ways away. But we have completed week 10 now, which is awesome. 10 weeks out of the 15 of the course. So, and this final project day, right, we've got a week after that last class, so which is nice. 428, is that what day of the week is that? 428, that's a Wednesday. Oh, that's a weird day, a Wednesday. Did I look that up right? I don't know. I'll double check that and see, but it should be the time slot they reserved for us. We can go from there. All right. So I don't have anything else today. If you don't have any other questions, we can go take a look and see who else we can bother on Twitch for fun. Send a raid off just for funsies and see who's around. If you have any friends online. You want to do math or rockets or music, art? Let's see. Or Dr. WD40 is making a bird feeder. We could go check him out too. Why don't we check him out? I haven't rated him yet this semester. Dr. WD40. We're gonna hang out there, say hi. He's one of the founders of the Knowledge Fellowship. So send him some love. And you folks take care. See you around.